Hello and welcome to Lecture 4 of Gauss's Law in Phys 1204. And in this lecture we're going to use Gauss's Law to do a few things. We'll derive the field due to a sphere, which we've stated before but never actually proved. We'll see that we can get another result that we already know but much more easily. And we'll use it to draw some conclusions about fields in and around conductors. Let's start this lecture with something which I'm sure has been keeping you awake at night ever since we first encountered it back in the E-fields unit. And that's that we stated without proof that the charge outside a sphere of charge is the same as the field if you concentrate that whole charge down to a point charge. I'm sure this has been bugging you. I know I haven't been able to sleep at night. So just to be clear, we're saying that if we're the same distance from the center of this sphere as we are from this point charge, so that's this distance r, then the E field here is the same as the E field here, so long as we are at distances greater than the radius of our sphere of charge. And we had no proof of this, and that's because it's difficult. Setting up a line integral, which you can do for a line of charge or something like that, is one thing. Setting up an integral over a whole sphere involves math that you almost certainly don't know. So let's do it instead using Gauss's law. So draw a Gaussian sphere, right? A sphere that divides space into an inside and an outside, and we'll put it so that our point where we want to know the E field is sitting right on our sphere, so it's a sphere of radius little r, and we make a symmetry argument. Our charge distribution has spherical symmetry, so does our E field, and that means the only way you can have a spherically symmetric E field is if it is the same everywhere on this sphere and perpendicular to the sphere. If it isn't perpendicular, then reflections break the symmetry. Well, so now we can write our flux. Gauss's law tells us our flux is the charge inside the sphere. Well, that's our whole charge on our spherical charge. So Q over epsilon naught, and that equals the flux. And the E field is the same everywhere on our Gaussian surface, and it's perpendicular to our area. And so that dot product just goes away. In other words, our area vectors are parallel to our E field vectors, so cos theta is a cos of 0, and the E field is uniform everywhere on the sphere, so we can just pull it out in front, and now we have an integral dA. That's just the area of the sphere. The area of a sphere is 4 pi r squared. Oh, solve that for E. La voila! We have that the E field due to our sphere of charge comes out as 1 over 4 pi epsilon naught q over r squared, and that's exactly what we got for a point charge. Just notice that setting up the integral with the methods we learned in the unit on electric fields is so difficult we're not even attempting to do it in this course. But using Gauss's law, we can make a simple symmetry argument and then 3 lines of algebra get us the result we're looking for. This is the real value of Gauss's law. In high symmetry situations, it makes life very much easier than just setting up the brute force integrals to calculate E fields. Let's just see briefly why the argument that we made for a sphere of charge doesn't work for other charge distributions. Here's a rod of charge Q, and I'm just going to naively stick a spherical Gaussian surface around it of radius r. That's a sphere, sure looks like a sphere. And it is certainly true, Gauss's law still applies, so the charge inside is the whole charge on the rod, and so Q over epsilon naught does indeed equal the flux, like so. However, remember that before we were able to argue that because our charge distribution had a spherical symmetry, so did the field, and so the E field was the same everywhere on the sphere, and moreover it was perpendicular to the sphere. But that argument doesn't work here. The rod doesn't have spherical symmetry. In particular, it lacks the rotational symmetries of a sphere. And so, for example, that tells us that the E field here is not the same as the E field here, and in fact we can't even guarantee that they're perpendicular to the surface. You could probably, if you think through it, see that they won't be. And so that whole argument fails, and we have no way of taking this E field, getting rid of our vector symbols, and putting it out front. And so all we have is this vague statement that, sure, this is something complicated, but if you integrate it over this surface, you get a nice simple constant. But that doesn't help us solve for the E field. Now that we've seen outside a sphere of charge, let's look inside a sphere of charge. Now, of course, there are many different spherically symmetric charge distributions we could make that would have charge inside the sphere. But let's look at the simplest, a spherical shell. So all of the charge is concentrated on the surface of a sphere, and we're looking inside there. And so as usual, we're going to draw a Gaussian surface that has the same symmetry as our charge distribution. So it's a sphere, and we make it the radius so that the point where we want to know if the field is right on the Gaussian surface. And notice, the charge inside that Gaussian surface is 0. All the charge is out here. And so our flux, which Gauss's law tells us is Q inside over epsilon naught, is 0. Now, there are many ways for a flux to come out 0 without the E field being 0. For example, you could have a uniform field so that the field in on one side exactly cancels the flux due to the field out on the other side. But that's not going to work here because, again, we have a spherically symmetric charge distribution, so the field has to be spherically symmetric, and we know what that means. That means it's radial and uniform everywhere on the sphere, which means we can pull it out front of our integral, and now this is just A, and the area of that sphere is certainly not 0. So the only way the E field times this integral is 0 is if the E field is 0. So the E field is 0 everywhere inside this uniform sphere of charge. Let's rederive something that we saw much earlier when we were looking at E fields, the field due to a plane. And the reason I want to do it again is that we found it before, but it was really hard. Think of what we had to do. We had to find the field due to a ring on the axis. Then we had to think of having many rings nested so that we could integrate over a bunch of different radii to get the field due to a disk. And then finally we had to let the radius of the disk go to infinity, and that gave us a plane. Well, we don't have to go through all this foo-fa-ra if we want the E field due to a plane using Gauss's law. So here is our plane of charge. And I've made it a positive charge, but that doesn't matter. And I'm going to draw a Gaussian surface. And it turns out that it really doesn't matter what shape I make this Gaussian surface as long as it contains a piece of the plane. I'm going to make it easy. I'm going to choose to make sort of a box that's passing through the plane. So what we're looking at here is the top of the box, but it passes through the plane, and so there's another bunch of it down here. And so it looks like that. And I'm just going to label the area of the end surfaces A, and there's some area of the sides that we might want as well. And let's now think about what Gauss's law tells us about this. So our total flux, we know, is the Q inside the surface over epsilon naught. And the flux is defined as the surface integral E dot dA. And let's think about that. That's going to be, we can split it up. You might see that the sides and the ends are going to be different. So these are no longer closed surfaces once you break them into these two pieces, but E dot dA sides plus the integral E dot dA, and I'll say top, and all the same thing for the bottom. The E field, we know from symmetry, has to have the same translational symmetry as the plane itself, and all the reflection symmetry and so on. That means it has to be perpendicular to the plane, and it has to be uniform everywhere. And the fact that it's perpendicular to the plane means it's tangent to the sides. And so this integral we know is 0. So that's gone. And now it's also, since it's perpendicular to the surface, it's also perpendicular to these ends. And so again, our dot products are just going to be an EDA with no cos theta. And E is uniform everywhere, and so once again, the E field is going to come out of both of those integrals. So we'll have E times the integral dA of the top, which is just A, plus, and the same thing for the bottom. So that's that. And that is all Q inside over epsilon naught. Oh, well, think of Q inside. If this area is A, then so is this area here. And so this is just eta A over epsilon naught, where eta is the charge density on our surface. Oh, look, we have a common factor of A on both sides, and so it's gone. And so we have 2E equals eta over epsilon naught, or in other words, E is eta over 2 epsilon naught, in 3 relatively simple lines with a symmetry argument. Contrast that with what we did back in the E-fields unit. I don't want to leave you with the impression that Gauss's law is only useful in situations where we're working with objects with high symmetry, because there are some very subtle uses of it that we can use to figure things out that would be difficult to figure out otherwise. So here's a really good example. Here's a conductor, and it's charged, but it's in equilibrium. So what do I mean? I mean there's no charge flowing around. It's all static. We've put it on, it flowed around to get to where it was going, and now it's stopped flowing. Now, without Gauss's law, one thing that tells us is that the E field everywhere inside here is 0, because think about it. If the E field was not 0, because the charges are free to move around inside the conductor, the E field would accelerate them, and the conductor wouldn't be in equilibrium. So the E field has to be 0 everywhere inside here. But now here's a trick with Gauss's law. We can define any Gaussian surface we want inside the conductor, and we know that the flux is the integral E dot dA, but the E field is 0 everywhere, so that flux is 0. And that tells us that the charge inside that Gaussian surface is 0. So right there we see, by a quick little argument, that all of the charge on a conductor in equilibrium must be out on the surface. None of it can be inside, because the E field being 0 and Gauss's law tells us that the charge inside any surface we draw in here is 0. Let's play a few more tricks with Gauss's law and a conductor in equilibrium. Let's suppose there's a bubble inside this conductor, and the conductor is charged. But again, if we draw a Gaussian surface around the bubble, we know, because the conductor is in equilibrium, that the E field is 0 everywhere out here in the conductor. And so again, our flux has to be 0. And so that tells us there is no charge on this inside surface. But now let's play an additional trick. Let's say that there is a positive charge Q trapped inside our bubble. I don't know, there's some little piece of insulator stuck in there and it's got a charge on it. Well, again, the E field in the conductor itself is 0, and so this flux still has to be 0, and so that tells us our total inside charge has to be 0, despite this positive charge inside the bubble. Well, so now what Gauss's law is telling us is that there has to be an equal and opposite charge, negative Q, spread over this inside surface that exactly compensates for that trapped charge there.